Welcome to this video tutorial about how to complete the Project 02 in MET-121. This project covers the plane circle-circle alignment. So looking at this print, I see we have a shape that is not rectangular, so that makes it not practical to use the plane line-line alignment. Well, looking at the datums on the print, I see that we have datum A is this top plane right here, datum B is this central 375 hole, and then datum C is this this right side 375 hole. So it looks to me like we have a plane circle-circle alignment, which is why this lab is named plane circle-circle. So let's put some thought into how we do the fixturing for this. Here we have our standard fixture plate shown in Mastercam. I like to use either Mastercam or SolidWorks to set up the fixtures because they have some great tools for moving things around. And mCosmos at least leaves something to be desired for moving CAD models around. If you've watched the webinar on PCDMIS offline, you see that PCDMIS has a great utility for doing a quote-unquote quick fixture that could be used to do the same thing that I'm doing in Mastercam here. One way or another, by the time you are complete with the fixturing, you need to make sure that your WCS or Work Coordinate System origin does match whatever you're going to do for your manual alignment. And on this part, the manual alignment will be a plane circle-circle, and that will put the origin directly at the center of this hole, so this is exactly what we want. Now, also looking at the fixture, I see that we have our 6 degrees of freedom constrained using a 3-2-1 alignment. The 3 points are the bottom surface of the part touching the top surface of the plate. The 2 points are the line that's created between the top tangency of this set screw right here and the top tangency of this set screw right here that prevents the part from rotating. And it also serves as our 1 alignment in this case as well. Notice that the part is pulled toward the operator in the Y- direction, so that way it contacts these screws. That stops both location and orientation, and we'll cover a little bit more on the theory behind this alignment later on in this video. So our CAD model has already been positioned on the fixturing. That'll make it easy to import into CAT 1000. And let's look at what we're going to do before we do it. So here's the completed program. I'm just going to show you all the steps, and then we're going to go do it in CAT 1000. So of course we start off with a subprogram. We load up our probe index, all that good stuff. And then we set our relationship to our CAD coordinate system. Now in between these two steps, we'll import that step model that we were just looking at with the fixture. And then we touch 2 different planes on the part. The limitation of CAT 1000 is it is not very easy to touch a plane all over without hitting this cap right here. So we're actually going to touch a circular plane over here and then another circular plane over here. And that is just an easier way of doing it. And then we'll connect the two after the fact. Now really that top plane there is just the base plane. We'll use that base plane to constrain 3 degrees of freedom. We'll do rotation about X, which is A, rotation about Y, which is B, and then translation in Z, which is the 3rd degree of freedom. So notice with our 3-point alignment, we are constraining 3 degrees of freedom. Now the next thing is we'll touch a circle, datum B, and that corresponds with the print right here. So we'll touch this central circle. And that central circle will end up being the origin of the program. So after we touch that central circle, that will be our 2 in our 2 part of our alignment. We will then create our origin in both X and Y. Then we'll come in and touch datum C, and datum C will be used to constrain our 3rd degree of freedom here. Now our 3rd degree of freedom is we can rotate about the Z-axis at this point. If all you have is the top plane and the central circle, this part could spin about that circle. That would look something like this, just to simulate it. Right, so we certainly wouldn't want our part to be spinning like this. If we don't have this last pin right here, we have nothing to butt that up against. So you see how it looks like that's stopping nicely at the top tangency of that pin. That's what we want it to do in the real world. So we touch that circle. Now, if you just have 2 circles, it really doesn't gain you much. In Mastercam, we had the part butt up against the pin on 2 different spots, and that created a line. So we have to virtually create this line in mCosmos, and then we can use that to constrain our C rotation with this alignment command right here. Now, of course, I'm just skipping over all these tolerances. We'll come back around to those in just a second. The last feature that we're going to touch is the circle on the left side. So that talks about the fixturing and the alignment. Now let's talk about how we're going to output all these dimensions. So if we were ballooning this print, we would have balloon number 1 is this 45-degree angle, balloon number 2 is this 1-inch distance, and balloon 3 is this other 1-inch distance. Balloon 4 would be this 3 times 375. So have we touched enough features to output all of these? Well, we did touch a circle for datum B, so that can be used to output one of these 3 holes. We did touch a circle on the right side. We used that for the alignment as well, so we could output the second one of these 3 hole diameters. And if you know where this hole is and you know where that hole is, well, that allows you to output the distance in between them. So it looks like the only other thing that we need in the program is we need to know where this circle is. Now switching back into CAT 1000, that is the left hole right here. And when we output the position of the left hole, it looks like we are not using our standard X and Y positioning scheme. If we were, we would have a linear dimension coming from the center of this circle to the center of this circle, and we would have some horizontal dimension readout here. And then for the Y-axis, we would come positionally off of here up to the center of this, and we would have some dimension going that way. It looks like here this has been dimensioned in a polar type fashion. So polar means length and angle off of some datum or reference. So because we've done this polar, after we touch this circle here, we also are going to have to create another connection element line between these 2 circles, and then we can output the distance in between, or I'm sorry, the angle in between this line, which is essentially our x-axis and our alignment, and this line over here, and that should give us that 45 degrees. So that's what's going on in the program. Let's get right into it. So I know it seems sacrilegious, but we are actually going to delete this program here, and we'll start again from scratch. So we'll start a new program. We'll name this plane circle, and we'll open up Learn Mode. It tells us that we're running offline. Of course, we're not connected to a CMM here. That's fine. And once Learn Mode is open, we'll switch back to Part Manager, and we'll open up CAT 1000. Now, we could program in either manual, CNC, or CAT 1000 mode. I think for this part, and most parts, it's going to be easiest to use CAT 1000, so that way we can take advantage of the CAD model. So we'll import the CAD model that I just completed. And there we go. It looks like this model is importing inside of the CMM by default. No worries. That is why we have not done our start block yet in Learn Mode. This way we can do our part alignment. Notice that that snaps the part and the fixture roughly centered on the machine's travel. Right? We can let it float in the air here. In this case, it's not an issue where we have to worry about fitting this part inside the machine's volume. We are going to create coordinate system number 1 when we do this, and we will say OK. And now we'll switch back over to Learn Mode and go Program, Subprogram, and Start Block. We'll say OK here, say no because we're offline, and skip over some of the other prompts here. Now the Start Block gives you a lot. It tells you what probe you're using, tells you that the probe is pointing down, opens up the dimension report format, and then it loads coordinate system number 1, and that is what we just established over in CAT 1000. So just checking to make sure, yep, our coordinate system does still match. So this load coordinate system number 1 is the same thing as doing a manual alignment. The rest of this is just setting some parameters in the background for clearance plane, etc. So that is all good to go. We do have to tell mCosmos that we are using that CAD coordinate system for our manual alignment here, and we'll just say OK. And now GeoPack or Learn Mode is linked up with CAT 1000 or CAD mode. So now we can start taking our measurements here. So it looks like we want to probe we could do an element plane grid here, but it's asking for a select complete edge. And really, we don't have any good complete edges to make a grid pattern that will get out of the way of this clamp. I mean, we certainly could try to finagle with these numbers here. We could do a 7x7 grid. Looks like the start point and end point would have to be modified pretty substantially to get that to work. And height 1 and height 2, we could probe over here and over here. Yeah, see, this really isn't working how we want it to work. What might be a better approach here? What might be a better approach is to scrap the element plane grid. You can see the graphic even looks like a rectangular part. We can scrap that idea entirely, and we can come over here to element plane circular, which is what I did in the last sample. So now we can select a circular edge. We can tell it that we want a full circle instead of just a partial circle. And then for diameter down here, we'll just set that to something that's roughly in between this diameter for the ID and this diameter for the OD. Ah, looks very nice. All right, so that gives us roughly what we want. Now we really would like to touch maybe another circle over here to distribute these points evenly. Maybe we'll touch 3 points on the left side and 3 points on the right side. And notice that this is datum A. So as soon as we touch that, we see a plane show up over here. This is datum A, but we're not going to do anything with that yet because that's only half of the story. You see that plane is really limited only to this side. We'll go touch another element plane circular, and this time we'll touch over here. We will set our, maybe we could set our start angle over here and our end angle. Let's turn complete circle off. We'll set our end angle over to here. So that way if this clamp is slightly misplaced by the operator and it swings over this way a little bit, at least our start point is not quite so close. We'll decrease our diameter here a little bit, and that looks like it's going to give us a pretty good representation of datum A, but really I'd like to connect this plane with that plane. So it's easiest to do that in Learn mode. We'll come up here and create another plane, and we'll name this datum A connected, and we want to make this a connection element. We'll do centroid and mean, our good settings there, and then we'll turn off all types of elements other than planes. We'll grab both occurrences of datum A, and we'll say calculate by measured points. So this is going to be our datum A plane. We'll come up here to coordinate system and align base plane. In this case, we will do our XY plane in origin and element. We'll make sure that that's pointing at the connected plane as opposed to the other two. And then we'll cancel out of the clearance plane when that comes through. Now looking back at the blueprint, we now have established datum A. When we go to do datum B as part of our alignment, keep in mind we can also use datum B for one of our balloons here. For balloon number, let's see, 1, 2, 3, that would be balloon number 4. 3 times diameter 375 plus or minus 5. So with that in mind, let's create an output text. So we'll say output text. This will be datum B, B4, or I'm sorry, diameter, comma, B4. Right, B of course stands for balloon. So it doesn't matter exactly what you use for a format here, but it should be consistent from one program to another, just so you can read your own work a year from now. And now that we have that output text as a nice label for the dimension report, we'll come in here and measure a circle. And in this case, probably 4 points on that circle is fine. Notice that we do have our fixture clamps inside of those holes, and those might get in the way. Let's see if we can turn off our solids here. Yeah, the height of those fixture clamps is pretty significant here. It looks like, it's not the easiest to see, but this is the top of the fixture clamp here. It looks like we're going to have to be very careful when we set this up, so that way that fixture clamp doesn't get in the way of this hole. I also want to measure this hole. Oh, let's switch this over to absolute, and we'll measure this at, let's say, minus 100 thousandths. And we'll recalculate that and see how that looks.